In this video, we'll be going through the topic 2 homework booklet. As always, make sure you're marking your work in red pen and watching through the method as to how we got to the answers, not just writing in the answers. Question 6 starts with this diagram, so we'll talk through this before we go on to the question. So we have got the electricity generation down the side in terawatt hours. Tera makes something bigger like mega, giga or kilo. If you want to look up the exact amount, you can check page 2 to have a look. Under your equation sheet, it shows you what all the letters stand for. And at the bottom, we've got all the years 2013 to 2016, and the Q stands for quarters of the year. Then we've got all these different colours to show us what's going on, or different patterns. We've got coal in black, grey is for gas, spotted as nuclear, dashed as renewables, and then oil right at the top. So question 1A, use the information in that diagram to describe trends in the use of individual fossil fuels and the total use of fossil fuels. So we need to comment on both of them for 3 marks. So if I zoom in on the diagram, first we'll start with the overall trend. So if you just look at the top of the bars, we can see that overall the trend is downwards. So you get 1 mark for saying there is a general downward trend in the use of fossil fuels over the period of time. But it's 3 marks, so we've got to say a few more things, and we'll talk about the individual ones. So if we have a look at oil first, oil is at the top, and if you just look at a few sections, you can see it is roughly the same. It's roughly constant. Or we could talk about coal, so that's this dark one down here, and we can see again, there's a downward trend overall. We don't need specific numbers, we're just talking about the trend. Or instead you could talk about gas. If we look at gas here compared to gas here, you can see there's a slight increase, although that one is a little bit harder to spot. So I've written in the answers there, general downward trend in use of all fossil fuels, decrease in use of coal, increase in gas, and stable in the use of oil. It will ignore any mention of nuclear. You might even lose a mark because it's asking about fossil fuels, not just non-renewable resources, specifically coal, oil, and gas. To get all 3 marks, you had to have said the first point and then 2 of any of these. And then for part II, the use of nuclear fuel for the production of electricity remains roughly constant, suggests possible reasons for this. So it's only 2 marks, so I probably would do the top 2 points here. That's nuclear power stations are running all of the time, and that there were no new nuclear power stations in this time from 2013 to 2016. But you can also comment on the fact that nuclear power releases no CO2. And for part III, it says production of electricity from renewable resources remained roughly constant. That's important. However, there's a reduction in the contribution of wind and a change in solar. Describe the weather in this period. So if wind has gone down, the contributions, it must be less windy. But because overall it's remained constant, we must therefore have more sun, or it must be sunnier in 2016. Part B is talking about CO2 emissions. So the important bits of information are that the original levels in 1990 were 3,900 million tonnes. Then we have a few different time periods and the targets and what the percentage reduction is. And we are calculating the percentage drop from all sources between 1990 and the end of 2022. So we first got to find the information that we need on there. So the target by the end of 2022 is this one here. So 2,544 million tonnes. And the original in 1990 is up here at 3,900 million tonnes. So we need to calculate percentage drop, which might be something you're more used to doing in your biology exams, or at least you will be by the end of the year. So what you're going to do is you're going to work out the drop first of all. So we do 3,900 take away 2,544, which is equal to 1,356. And then we're working it out as a percentage. So we take that answer, 1,356, and we divide it by what we started with, but it's a percentage. So then you times it by 100. And you get 35% if we round it to the nearest whole number. And that's just because nothing else has got decimals in the question, so the nearest whole number sounds sensible. And the last mark talks about how we're predicting by the end of 2022 to have fallen by 40%. However, we're hoping for a 50% reduction. So it's saying sort of comment on that progress. So you want to say it's good progress because 40% is getting close to 50%, but obviously it's not quite there. However, you might want to consider that some things have not been factored into this. So it's talking about the fossil fuels and what CO2 they produce, but it's not talked about things like heating in houses that produces CO2, and I've specifically mentioned cars in that answer. And here's a screenshot of the mark scheme for that question, so you can see exactly where the marks are. In lesson 2, we're looking at efficiency and different types of power station. So we have 4 different power stations here, A, B, C, D. We can look at their efficiency and their rank, their running cost and their rank, and their emissions and their rank. So the question is saying, Gareth says the best type of power station is type B. Do we agree? And if we have a look at type B, we haven't got the efficiency, but we know it's the best. So the ranking here means this will be the best one and this will be the worst efficiency. It's got a practically zero running cost, which is the best out of all of these, and the emissions, it's got no emissions, again putting it the best. So you just have to make sure you word this carefully. You want to say you agree, because type B is number 1 for all features. And moving on to the next page, we're still going to use that information, but now we've been told that they represent fossil fuel, nuclear, and hydroelectric. So there's only 3 power stations there, but we have got 4 different power stations. So we're going to need to use one of them at least twice, but it does say we could use or each of them once, more than once, or not at all. So if we have a look at this, the first one that I think is the easiest to notice is type D, says it produces radioactive waste. So therefore, that one is going to be nuclear. And type B that we've just been discussing is the best, has no emissions, so it's going to be hydroelectric. The 2 that we have left both emit some sort of emission. We're presuming CO2, it doesn't say, but we're going to presume so, and different amounts. It's most likely that those 2 are different kinds of fossil fuels. So I'm going to write fossil in for both of those. For example, one could be gas and one could be oil, and that's why there'd be different amounts of emissions. And part B, we're calculating the efficiency of a type B power station. If you remember the equation for efficiency, you can always check page 2. It is the useful energy or power divided by the input or the total times 100. So you just need to know about power stations, what's useful, what goes in, and what is wasted. So our input energy is 200,000, the heat is 30,000, and the electrical energy is 170,000. So what we want from a power station is electrical energy. So that's going to go on the top, and we're going to divide it by what goes in. They are both in megajoules. We don't need to worry about converting because they're both the megajoules, but don't forget we also need to times it by 100 because it is an efficiency. And this gives us 85%. And here is the mark scheme so you can see where the marks are. Homework 3 is about the national grid, and we start with the 6th marker. Describe how the national grid provides a reliable supply of electricity as efficiently as possible. So you want to make sure you mention reliability and efficiency in this answer. So we've started with a definition. The national grid consists of a network of power stations, transformers, and power lines all joined together, supplying electricity to consumers. Supply and demand is monitored. At times of power station failure, electricity can be transferred from one part of the grid to another. At times of peak demand, reserve generation can increase supply, or electricity can be imported from abroad. Transformers are used to step up the voltage before transmission along power lines. This reduces current and power loss as heat in the cables. Then we've got a lot of data about the national grid, and it's asking for the efficiency. So we're going to start with what hopefully we remember or can look up, the equation for efficiency. So it's going to be our useful output divided by our input times 100. So we're going to look through all this data and see if we can find an input somewhere or an output, either useful or wasted could be important. So I would start with the maximum demand because it does say maximum demand. So that is going to be our total or our input energy. So that's going to go in there, 63 gigawatts. And I'm not going to forget that it says gigawatts because not everything does here. And then to find our useful energy, I think the easiest way is to start with that 63 again and take away our total losses. However, they're not in the same unit. So what you do have to realise is that gigawatts is times 10 to the power of 9 and megawatts is times 10 to the power of 6. So to work out the difference, we'll do 63 times 10 to the power of 9, take away 1,420 times 10 to the power of 6, and then we'll work out how much we've got left when we take away what we've lost from what we started with. And what you get straight from the calculator is 6.158 times 10 to the power of 10, and that's just in watts because I've gotten rid of the giga and the mega, etc. So that is my useful. I need to divide that by my input. So I'm going to do this answer of 6.158 times 10 to the 10 divided by 63 times 10 to the power of 9 because it's in gigawatts times 100. And the answer that I get is 97.7%. Then the next question is asking us to do power is energy divided by time, the annual mean power used in gigawatts, that's important. So looking at the previous page of data, I just looked for any data point that mentioned energy, and this is the only one that mentioned energy. So we have 360 terawatt hours, and the first thing I'm going to do is convert it into gigawatt hours before I even worry about the time. Okay, so the difference between a terawatt and a gigawatt is times 10 to the power of 3. So what we're going to do is we're going to write 360 with 3 zeros in the end times 10 to the power of 9. That is equivalent to this up here, 360 times 10 to the 12. So that is 360,000 gigawatt hours. So I've converted between those units. If you can't do that, do not panic too much. You can still do the next part and you might just lose 1 or 2 marks. And then we're going to divide that by the time, and the time in hours is just for 1 year, so it's actually going to be 8766 hours. And the answer that you get is 41.1 gigawatt hours. Very hard question, don't worry if it's a bit confusing. And then the last bit, tick the boxes next to 2 correct statements about the data opposite. So number 1, at maximum demand there is a spare capacity of 16.9 gigawatts. That is true. The maximum demand is equivalent to 85%. Nope. The difference in maximum demand between the summer and the winter is approximately 10,000 megawatts. So you need to look at the diagram, measure things, do a bit of taking away there, but that one is true, that is not true, and that is not true. So for our revision question, first part is asking describe how electricity is produced in a fossil fuel station. You've got to be really specific with the words you use here. So you've got to say the fuel is burned, that's an important word to get the mark, to boil water into steam. It's not smoke that powers our turbine, it is water and steam. The steam turns and rotates a turbine, and the turbine turns a generator which produces the electricity. Part B is a Sankey diagram question. This is quite a hard Sankey diagram question, and there are lots of different ways to answer it, but I'm going to answer it in the way that makes most sense to me, and the mark scheme's on the next slide if you've answered it a different way. So first of all, I've written down our efficiency equation because that's going to be important here. And we've got 75% of our input energy is transferred to being useful energy. Of that, 40% is then transferred to the national grid. The input, or Helen estimates the input is 20, and the output is 3.2. We know that they're both in megawatt hours, so that's not really important here. And we just need to confirm whether these numbers add up all together. So I'm going to start with what Helen thinks it is, work through to the answer and see if I get an answer of 3.2. If I don't, she must be wrong. So I'm going to start with my 20 megawatt hours, and it says 75% is transferred as useful energy. So I'm going to times it by 0.75, which is the same as timesing it by 75 and then dividing it by 100, and I get 15 kilowatt hours, and that's our useful energy. Of that, only 40% is then transferred to our national grid. So I'm going to do 15 times 0.4, which is the same as working out 40%, and you get 6 kilowatt hours. This is not 3.2 kilowatt hours. So therefore, I think Helen is wrong. If you've done another method, you can check on the next page on the mark scheme to see whether you would have got the marks. And here's the mark scheme for that final question. We only did parts A and B.